Okay. Hello, everyone. My name is Chewan, and this semester I've been working on this personal project where I try to see how the attention mechanism helps reinforcement learning tasks in making it more interpretable and also boosts its performance. So, table of contents. First of all, I'm going to explain the motivation and the concept of XAI using various examples. And also, there's different ways to implement XAI, but I'll be focusing on the concept of attention. So I'll show how attention can help reinforcement learning agents by taking examples from the survey study that I did. And then I'll introduce the problem statement that I'll be researching. And then to better elaborate on it, I'll need to go into technical details of the attention mechanism and the model structure that I'll be using and how I implemented it, and later on discuss the experiment results. So this is a comparison chart between the conventional machine learning and explainable AI. So you can see that the top is the conventional machine learning, where we throw in a bunch of data, it learns the pattern embedded into these data and be able to solve the task. But there is this downside in that it is quite hard to understand what the model has actually learned. It is black box in that we know the result, but we don't know how it got to that result because there's so many parameters, nonlinearities, and layers in the deep learning networks that it's difficult to translate into human interpretable information and language. So for instance, if there is like a CT scan and you're using machine learning to see if there is a tumor or not, it will tell you that there is a tumor or not correctly, but it won't tell you how it got to that decision. While if you talk to a human doctor, the doctor will explain in very intuitive human words of like why of his analysis of that CT scan. So that is like the difference. So you want this neural network model to be more like the human friendly interfacing doctors in that is able to provide an explanation that is very intuitive for the humans to understand. And there's so many ways to implement this explanation, but I'll be focusing on the attention mechanism, which I'll be explaining further on. So some concrete examples that might help your understanding. So this is images of CT scans, and this is for medical diagnosis of some disease. You can see that there's some red areas and blue areas. And the red areas are basically heat maps on the areas that has contributed heavily to the model's prediction. So if this is a diagnosis for disease X, then this red area has contributed a lot to that diagnosis. So normally, you just looking at the CT scan, we won't be able to know anything, have no clue on how it diagnoses disease. By having these color-coded heat maps, we know which areas that the model focused on and where we need to really pay attention to. And this is implementation in autonomous vehicles vision systems. So we want to correctly and robustly identify pedestrians and cars where the heat maps have correctly identified. And this is very well aligned with the human driver's perception. So in the case that we see that the attention map is on the sky or on the road, we know that something went wrong with the training. And we're able to input logic or mechanisms to make sure that the model is learning from the right features and be able to nudge it into that direction. And this is also an example in NLP regarding sentence translation, where when translating each word, we pay attention to neighboring context words and then calculate its like similarity one by one. And then we weight those similarities with the word embeddings to capture a context vector. And that context vector is used to provide a richer context in translating this specific word. So this color code kind of shows the degree of similarity. So the advantages is basically that, explainable AI, it's making the neural network model more human-friendly, more compatible with humans, in that it makes it easier to debug errors and find error causes and for us to fix it before a huge failure happens. And this is very important for safety-critical applications like autonomous driving or medical diagnosis or in finance, et cetera. And also it helps provide intuitive explanations. And this helps build social trust and acceptance, which helps us commercialize and get our products become of a public usage more intuitively. And it also increases model performance in that attention not only provides interpretability, but also boosts the model performance in terms of accuracy and generalization. And now more focusing on to how it helps reinforcement learning. So this was an interesting paper that I read called Neuroevolution of Self-Interpretable Agents, which I found during my survey study. So you can see that there are some white patches on these videos. And it's that the white patches are where the model is paying attention to. So in the self-driving, in the car racing example, you see that the car is paying attention to the curb side of the road when it's making a turn, so that it makes sure that it's not going out of track when it's driving. And in the shooting game, it's paying attention to the walls or the enemies. So in the case that these patches are on the wrong areas, we know that the model has been trained with a wrong logic, or the model is looking at the wrong features of the observation frame. So we're able to debug it and fix it and make sure that our model is really learning the things that we want it to learn and really eradicate biases or those mishappenings. And how this is done is that, first of all, they kind of cut these images into different patches. And by using self-attention, it kind of calculates the similarity and also weights it to get the context vector. So you can see that the red areas are the heavily significant ones, and the blue ones are like backgrounds that it just not pays attention to. And this is like the diagram of the flow where we flatten the patches, use queries and keys to calculate self-attention, and is summed along the columns to get the importance vector. And this importance vector is weighted to create these features and is used to produce these actions. So the problem statement here was that in these models, they basically just do a dot product between the queries and keys. I thought that although that is a widely used similarity metric, it might not be intricate enough to capture the different nuances in the observation frames, because it is really rich with various information. So I wanted to implement 5 different kinds of different attention mechanisms and see how it impacts the model performances. So this is a quick recap or overview of the attention mechanism. So when we are calculating the context vectors, C1, for predicting this word S1, we calculate the similarity between H1 all the way up to HTX with this target S1. So either doing a dot product or different kind of similarity functions, we're able to produce these alphas, and of course pass them through a softmax layer to make sure that their weights sum up to 1. And then by weighting H1 with alpha 1i, we're able to do this weighted sum and get this CI. And by using C1 and also this previous embedding Si-1, we're able to calculate this new S1. By using it, we're able to calculate Y1. So basically, attention mechanism helps provide a better, rich context that is most relevant and necessary to understanding what this vector means in the context of the entire picture. And there are various kinds of attention mechanisms. This is most prevalent, the dot product. But there's other variants like the scale dot products, where you divide it by root of n, and n is the dimension of the vector st dot si. And we do this because we want this variance to be equal to 1. And there's additive attention, where we concat s and h together and pass it through a series of linear and nonlinear functions so that hopefully W and B can capture those relationships. And there's content-based, where we use a cosine similarity, location-based, where we want to only use S rather than H, so that it has more weight on what we're actually looking at. And there's also this mechanism of using query keys and values, where we, instead of using the raw S and T, S and H, we multiply it with these matrices, hoping that this will provide a stronger degree of freedom that captures different nuances. So when you are multiplying the queries and keys together, you could use basically the same raw versions, but maybe providing this degree of freedom may capture different nuances that might somehow help capture a better representation. And this has actually been proven in many papers to work really well. And this is the overview of the model structure. So this model uses the Impala structure algorithm, and also is an after critic setup, uses the V-trace loss, and uses the RMS prop for optimizer. And has this intricate structure where it first takes in the observation, and then the vision core kind of extracts feature maps that can be split into keys and values. And these are the keys and values I've explained in the previous slide. And because later on we spatially reduce it, the positional information is lost. So we kind of have to concat spatial basis to these keys and values to make sure that we know which features correspond to which areas of the pixels. So after we concat them, we have a query network that outputs the query. And then we do a dot product between the queries and keys to get our alphas, which is the attention map. And then we multiply it with the values to get our context vector, which is then spatially reduced. We put it into the LSTM and get our output. And what is special is that in the query network, we're not inputting the observation itself, but we are inputting the output of the LSTM. And this is really interesting because usually we think providing more information to the query network will give a better query. But in fact, this may just inputting the observation may overwhelm the model. So instead we use the output of the LSTM, which is a smaller dimension, more condensed, more abstracted, more selected with thanks to the LSTM. So it helps the query actually become more simplified and also more efficient. So it becomes less overwhelming for the model. And also another interesting finding is that this model is able to differentiate between content and spatial channels. So if you visualize what the content channel has learned, it has attention maps on the what, which is like player, enemies, and scores, while for the spatial channel, if you visualize it, it's more on tripwires and tracing paths of enemies. And by tripwire, what it means is that it has attention or is monitoring certain areas of the observation frame. So once something like the enemies or the ball, the moving ball, like passes through that area, the attention now suddenly all focuses onto that moving object or the enemy. So it kind of alerts the players to now focus on those enemies or the ball because it has become much closer to the player itself. So it's a really cool alert system that the attention mechanism is acting as. So this is shown to be very robust, unseen frames, and especially no trade-off between model performance and interpretability. This is really important because usually performance and interpretability are an offset. Interpretable models like linear regression, their performance is not as good as neural networks, which lacks in interpretability. But this model captures those two aspects greatly without any offset. And also compared to non-attention-based agents, the attention-based model is able to focus more on future trajectories and also value functions that really think about those future rewards as well. So this is the experiment results that I did. So I've implemented 5 different kinds of attention, and this was the parameters that I tried. Number of actors was 4. It trained for 50,000 steps, and the unroll length was 50, where I trained for 50 steps and then send the experiences to the learner to update its weights. You can find the code in this link as well. So overall, I saw that, interestingly enough, with the basic model, content-based, which use cosine similarity, showed the highest reward. And then once I added the LSTM and buffer to the model, then it kind of flattened out to be very similar to one another. And my original hypotheses that maybe using advanced attention mechanisms like additive attention, where I use 2 linear layers and also relative activation, would do better, did not actually prove to be true. It actually showed that the dot product, which is quite the simplest, did fare as well as the other 5 attention mechanisms, although it did kind of drop when we added more intricate mechanisms to the model. So overall, some of the analysis I was able to make was that the simple similarity functions like dot product or cosine similarity is sufficient to learn attention weights. And so extravagant similarity functions is not really a necessity in capturing the correct alphas. And also one thing that I have speculated is that maybe using the LSTM buffer did not show much improvement because the attention mechanism was already capturing those improvements on its own. So the impact of LSTM buffer might not have manifested as strongly. And lastly, because due to the GPU resource limitations, and I had to train 5 different models every time, training for longer episodes was a bit difficult. But I think that maybe training for longer episodes and number of episodes might be quite crucial in seeing the model to fully converge and actually helpful in verifying my hypothesis better. So this might be another future work that I might try in the future. Thank you. This is the end of my presentation.